Well, hi there everybody. It's time to continue with the second last in our series of complex regions, which is just a name for complex numbers loci. And today we're going to look at the fabulous world of the ellipse, the amazing, beautiful, synchronistic ellipse, which is really a bent circle, an egg, an oval, and it's a marvellous, beautiful thing. So let's have a look at it. Okay, now I'm going to use a case study for you today, and the case study that I've chosen is this beast here. Okay, it's not a beast, it's a beautiful creature. That is the form of that equation is the form of an ellipse. An ellipse is really very closely related to a circle, and if these numbers down here were equal, say this number here was 5 squared, then being the same as this number, that would actually be a circle. But the minute these numbers are different from each other, that means that this distance here from the centre to the outside along the x direction is different from this distance here, which is the length in the y direction from the centre to the outside. That's what happens. And then you have to call this x distance here the x semi-axis now, because you can't really call it a radius anymore, because a radius is when the distance is the same, always from the centre to the outside of the circle. So this one here is the y semi-axis, okay? And the x semi-axis is a number under the x, but it's squared, and the y semi-axis is the number under the y, but it's squared. And you can see that in this instance, the x semi-axis, according to this scale, is 5, and the y semi-axis is 4. How marvellous! So now, let's have a look at the locus form of this beautiful creature. Okay, so what have we got here? We're saying that get used to the look of this, because that's what you need to recognise more than anything else. You need to recognise when you've got an ellipse. So we're saying that there's the distance from z to the point 3 on the x-axis, plus the distance of z to the point -3, remember that's minus -3, has a combined distance always of 10 units in this case study. So these points here, which I've marked in for you, they are called the foci, okay, plural of focus, okay, there it is, okay, they are the foci, and that's the way I've written it for you, so that you can see the distance of z from -3, and plus the distance of z from 3 is equal to 10 units. So I can really say that PB plus PA equals 10. Now, what I want you to do is imagine we've got a piece of string, okay, and we're going to thumbtack one end of the string into this point here. Hopefully it doesn't damage my iPad. I think I'll have to go and buy a new one after this. And we're going to thumbtack the other end into this point here, which is where x is +3. And this string, the length of this string is exactly 10 units long, okay? And you'll notice that that's possible because this is the distance from here to here is exactly 6. So we've got some slack in the string, and we're going to pull this string tight with a pen, and the shape that we're able to trace out with that pen will be the ellipse. It will work just like that. Okay, so there's another way that you could move the string slightly to the right, and the combined distance back to A and back to B would still be 10, and you would still be on the point of the ellipse. There's another one, okay? You're getting the drift? There's another one, okay? And this one over here, now that's an interesting one. That goes from in the horizontal, so that goes from A all the way over here to the point on the, well, if I call it the circumference, it's not really the circumference anymore, but you know what I mean, on the edge, on the locus, and back to B. Okay, that's 10 units long. Here's another one, yes, and there's another one. Okay, all of those comply. They're all those points P are on the ellipse, on the locus, and the combined distance back to A and B is always 10 units. So that's what I've now described the intuitive geometrical significance of this whole thing by this piece of string anchored at A and B and pulled tight at P by a pen, okay? And the path traced out by the pen is the ellipse. Is the ellipse, all right? So the length of the string is 10 in this case, okay? In this case, right? But it always has to be greater than the distance from A to B. That's what I'm saying in this sentence here, okay? That's the thing you've got to check first. Is the distance, is the length, is this number greater than the distance between A and B? And if it is, then you've got yourself an ellipse, okay? Right, now, let's just continue with that a step further. If the string length equals the distance between A and B, then what you've actually got, if you think about this, say for example that the distance, the length of the string was moved down to say 8 units. Well, the string would be tighter because the string is not as long. Therefore, you'd have a tighter orbit around these foci, wouldn't you? Yeah, you'd have a much shrunken ellipse. If you move that down to 7, you'd have an absolutely really tight ellipse, hugging these points and just sort of orbiting very closely around them, wouldn't you? And the limiting case is when you get right down, the length of the string becomes the same length as this number here, which in this case would be 6. In that case, you've got a straight line because the string is pulled tight and exactly between A and B with no slack in it whatsoever. And then the last but not least case here is if the string length is actually less than the distance between A and B, then you've got no solution whatsoever. No solution is possible, okay? That's the thing to watch. Now, this is what they want you to recognise in an exam setting. They don't necessarily want you to actually work out the equation from here. From this equation here, our objective in a minute will be to get to this equation here. But that's not what they want you to do in exams because it takes too much time and it just soaks up valuable testing time where they are not able to test you on a whole wide range of things, which is what they want to do in exams because you're bogged down doing all this algebra. So get used to recognising the form of an ellipse, okay? A distance to one point plus a distance to another point equals a number of units, and that number of units has to be greater than the distance between those 2 points. Right? I've said it about 3 times now. Right, now here's our ellipse. Now we're going to go through the general equation, the general algebraic equation for, that's Cartesian equation for an ellipse, okay? Now, you've got an equation over here. This one's not in its most general form though. The most general form is here, where you've got the centre point of the ellipse, the centre, that's H and K, okay, and the X semi-axis is A, distance from the centre to the outside along the X-axis, and the, or basically even if it's not on centre, it would be the distance horizontally from the centre to the outside, right? This is the distance from the centre to the most vertical position, okay? The Y, or the vertical vertex, if you like. Highest vertical distance from the centre, and that's the centre point is H and K, okay? So there it goes. Now in this instance, H and K happen to be the origin, but you know they don't necessarily have to be if the thing is off centre, okay? A is the X semi-axis length, right? Which used to be the old radius, but in the X direction, and that's 5 in this case. Yes, I've marked it in. And B is the Y semi-axis length, okay, vertically, and that used to be also the radius for a circle, but it's not anymore because we've got a bent circle because these numbers here are different from each other, okay? You get that? Very good show. Okay, so let's move along. Now, note that the Cartesian equation for this ellipse, note that equation above right. I've been referring to it anyway, so you've been noting it. Now, our objective is to find this equation from our locus equation here, okay, from this equation here, both using algebra and secondly using geometry. That's what we're going to be doing in this session, and then I'm going to do a few examples for you, okay? Then we'll be well and truly used to ellipses, but I'm going further than what you would need to do for an exam setting because then you will be able to pull back from that into just recognition mode and with confidence. I always think it's better to learn a little bit more than what you need to just gain that little edge of confidence and therefore psychological advantage. Okay? Confidence is everything, guys. Confidence comes from practice, and practice comes from lots and lots of good, solid work. Okay? Which is not work if you enjoy it. Now, what I'm saying here is my little caveat, okay? I'm saying that the exam question focus, which I've been just saying before, is not on solving for the Cartesian equation of the ellipse. You don't have to solve it in the exam, it takes too long, but on recognising the form of the locus of the ellipse, okay? So if I said to you, if I change that number into a 5 there instead of a 10, you should be instantly able to say to me there's no solution. There's no solution because the 10 is less than the distance between plus 3 and minus 3. Yeah, you get that? Now, okay, here it is, right? Here is the ellipse that we've been dealing with, our case study, and here we're going to do the geometric way of getting to the Cartesian equation. This is pure gold, this method. The algebra is pure sludge, as you'll see in a moment. Now, this is there's my caveat again. This is for the purpose of information and comprehension rather than for exam preparation. Okay? Alright. Now, the first thing I've got to prove to you before we even do the algebraic solution, see this number here? That number is twice the semi-axis on which the foci reside. It's twice, I'll say that again. Now these foci reside on the x-axis, okay? Right? In the horizontal orientation, right? Yes. So that's where these foci reside. So therefore this number here is twice the distance from the centre of the ellipse to the outside horizontally. In other words, the distance from the centre to the outside horizontally must be 5. Now I'm going to prove that to you, okay, in this, so that you'll always be confident in that knowledge, okay, because that's part of the way we solve this thing. Now, I've drawn a few little points there of reference so that we'll know what we're doing, and I'm just defining this in very clear terms. I'm saying here that 10 is twice the length of the semi-axis on which the foci are situated or sit, okay, or reside. Get that? Now, again, I want you to think of the piece of string. Okay, I want you to imagine that in this case the string is taut at C. So we're going from A all the way over to C and then back to B. Now, if I can prove, ladies and gentlemen, that gets you the length of the string, but in a horizontal orientation. If I can prove to you that that length of the string is the same as the length of D over to C, which, as you can see, is twice the length of the x semi-axis, because it's the whole way across from one end to the other, then I've proved it, haven't I? I've proved that the length of the string, if I can prove that the length of the string is the same as the length DC, then I have proved that the length of the string is twice the length of the x semi-axis in this case. Yeah, x semi-axis in this case. Haven't I? Good. Alright, now, in order to do that, I'm going to say let DA and BC, which are the same length by symmetry, let them be x. Okay? Therefore, they're both sitting there and they're both x. Now, the length of the string, here we go, in terms of the parameters which I've just defined, it goes from A to C, as I showed you before, and back to B, right? Now, okay, so AB plus x plus another x, right? Now, that is exactly the same. That's 10 in this instance, yes. It's exactly the same as the distance from D to C, because D to C is, in fact, x plus A to B plus another x. So it's the same length, right? The same as the string length. So therefore, I've proved to you that the string length is actually equal to twice the x semi-axis, right? So therefore, now you can just take that knowledge now and into the future and always use it, okay? Yeah, in this case, 10 equals 2a, yeah. Okay, so a is 5, very good. And there's that immediately, just from looking at your locus expression, you can put that number in there, You see that number, you say, okay, these foci reside on the horizontal semi-axis, don't they? And therefore, this number is twice the horizontal semi-axis, right? Which is 5, and therefore you put that straight over there under the x term as 5 squared, and you're done. Now, okay, the next thing we do is to find the centre. The centre of this ellipse, right? Well, it's pretty obvious, isn't it? Look, it's halfway between here and here, isn't it? Yeah, so, okay, so if you take the average of plus 3 and minus 3, to add them up together and divide by 2, you get this number here, which is 0, and that is the centre point. So therefore, now you know what goes in the H and the K space, which we defined on the previous screen, which is 0. So you just get the x minus nothing squared, or just x squared, y minus nothing squared, or just y squared, because the centre is at nothing, or the origin, if you like. Now, so that's what I've said there. You just take the midpoint between the foci, A and B, and that's 0 in this case, right? Now, to find B, which is the only thing we've got left to find, which looks like it has to be a 4, but we're going from here, you see. We're going from here to work this out. We do a bit of marvellous Pythagorean skullduggery, okay? So, I'm going to show you a symmetrical version of the string. Now, see, this string is 10 units long, and I've made it symmetrically. I've pulled the pen tight so that it's symmetrical, and this point here is equidistant from A to B, and therefore the string length is the same either side of this apex here where I'm pointing with the green arrow. So therefore this would have to be 5, this length here would have to be 5, that length there would have to be 5. And obviously we've got a right angle triangle here because the orthogonal axes are orthogonal, they're at 90 degrees to each other. Therefore, see, look, this is 5, this is 3 after all, because A and B are at points 3 units distant horizontally from the origin. Therefore, by Pythagoras' theorem, this length here, this vertical length, must be the square root of 5 squared minus 3 squared, which will get you, what will it get you? I'm just going through it all now. There it is, and it's equal to that, it's equal to that. Therefore, it equals 4. B squared is 16. B squared is really the number that you want, okay? So, therefore, there it goes, okay? 4 squared, or 16, and there is the end result. Now, I did that very, very elegantly and very simply with geometry, okay? It was very easy. Thank you, Mr. Box. Do you see it, and do you get it? It's very, very mighty fine. Now, okay, we're going to do the algebra method now, so get your chill pill ready. It's going to be very confronting, to say the least. Okay, this is for the purposes of information and comprehension rather than for exam preparation. Okay, so here we go. Now, this is the same procedure that we've been using all along when you do it algebraically. Okay, you go into a modulus mode if you've got a modulus statement, and then you get your ducklings in a row where you get your reals and your imaginaries together, and like that. We've done that. Now you Pythagorate it, like that. Now, you have to be aware that you have got to put one of those square root signs over the other side. Otherwise, you are going to end up in an impossible mess, which you'll be so deeply ensconced in the algebra mud you'll never get out, I can tell you. So we'll do that to save our lives. Yeah, it doesn't matter which one you take over the other side. I've taken this little guy here. Okay, I've taken him over the other side, haven't I? Yes, now we're going to square both sides. So get ready. Now, you've just got to go very slowly and double check everything that you do. Do not neglect doing that, otherwise there's so much processing going on here. It's just extreme, okay? And there's so much opportunity there for error and falling in a ditch that, you know, if you're ever going to do it, you'll do it here. So don't do that. Keep multiplying out, create an enormous sausage machine, which is truly something to behold. Now we'll start cancelling, okay? The x's cancel, x squareds, I mean, the y squareds will cancel. It looks like the 9s will cancel as well. That's pretty good. Now we've got to clean up now, mop up after the cyclone, after the typhoon or the hurricane. Now, here we go. I always look for a common factor. I think I'm going to divide by 4. That would be a good idea, because then we'll end up, if we don't divide by 4, we're just going to end up with telephone numbers when we square both sides again, and I'm not particularly interested in telephone numbers. The only purpose of telephone numbers is for ringing up, not for trying to do algebra with. So now we get to that. Is that right? 4 into 12 goes 3, 4 into 100 goes 25, 4 into 20 goes 5. Yes. Now we can square both sides now. Okay? And let's do that. Let's do the yes, my little helper. He's feeling the strain. I can totally sympathise, little helper. Go and get an aspirin. That'll help, I think. Now, is that right? Yes. Did you notice how I remember to square the 5? A lot of students forget to do that to keep us alive. So the algebra can thrive. You have to do that. Let's now square both. Let's square the left-hand side out and multiply the. Oh no, I've left the bracket on the right-hand side. Okay. Now we'll get everything out with no brackets. Good heavens! Look at those numbers. Good gracious. Well. Oh, look at that. The 150s are going to cancel. Beautiful. Well, that's a nice result, isn't it? It's looking nice, and there's a synchronicity about it which is appealing to me. I think we're getting to the right answer. All right. Does that look right? Yes. Now we're going to put it into plus terms, and now we're going to divide both sides by 400. Yes, and I think that's going to be the result we were looking for. Yes. Oh, yes. How sweet it is. How sweet it is. We've navigated the rocky algebraic road. We didn't fall into the ditch, and we got to the end result. And boy, oh boy, are we happy. Look at that. That's the same beastie as up here, guys, and we did it. We did it with all the algebra. Algebra City, USA. So, as I said to you before, you don't need to know exactly how to do this, but it's jolly good practice for you if you do it, because you gain enormous confidence from doing stuff like this. Okay? Then you can pull back to recognition mode, like I said, and with confidence in the assurance that you know what an ellipse looks like. Okay? Now there's the finished product. I've got that. That's the y-intercept, and that's a y-intercept. And this one's an x-intercept, and that's an x-intercept. All very easy because this thing's on centre. The centre is at the origin. If the centre's not at the origin, it's more tedious to find the x and y intercepts, but it's still perfectly doable. You just have to spend a bit more time doing it. Okay. Now we're going to go into further example mode here. This one here, that's an interesting looking beast. See, I automatically know what that is, guys, and you should be able to too by looking at that. I'm not going to give the game away yet, but I can tell you that is not an ellipse. This one here, right. I can also tell you that that's not an ellipse as well, just by looking at it. This one here, and what do we got here? That's z minus, so that's the distance of z from 6i, plus the distance from z from minus 2i. That's 8 units apart. Yes, ellipse, 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 that's an ellipse. Okay? So, you get what I'm doing? See, this one here, the distance between I and minus 2i is 3 units, right? Now look at the number on the right-hand side. Okay? For an ellipse, the number on the right-hand side needs to be greater than 3. Now, because the distance between I and negative 2i equals the number on the right-hand side, this is a straight line. It's not an ellipse, it's a collapsed ellipse. Okay? Joining the points I and negative 2i. I. So the equation we're looking for is, okay, it's because these 2 points here, these 2 foci are on the y-axis, okay? So the line we're looking for, the straight line that we're looking for, is the y-axis, which is x equals 0, okay, because it's a straight line between them. But you've got to put this constraint in here, where y goes from negative 2 and including up to plus 1 and including. That is your answer. Thank you, Mr. Box. Okay, how are you going? You get that? Good. Let's do the next one. This one here. Okay, now the distance between 6 and negative 3 is 9 units. And look at the number on the right-hand side. Oh, gasp. It's less than 9 units, right? See? So therefore, this is less than. Therefore, what have we got? No solution. No solution whatsoever. There's no locus in the universe that I know of that'll fit that, okay? At least not on planet Earth anyway. Now this one here, because the distance the distance of Z from 6i plus the distance from negative 2i, which is 8 units apart, is equal to 10. And 10 is more than the 8 units, therefore that is an ellipse. But this is an ellipse where the foci are residing on the y-axis, okay? So I could sort of call that a vertically based ellipse, if you like, rather than a horizontally based ellipse. So we're going to do this one. It's an interesting one too. Okay, 10 is greater than 8, therefore yes, we have an ellipse. And we're going to go geometric, because that's my favourite preferred method for obvious reasons based on what we've just been doing. Okay, so the first thing I can say is that in this case 2b equals 10, right? 2b equals 10, because the axis on which the foci reside is the vertical axis, right? So therefore B is 5, okay, not A, but B, okay? B is 5, okay? The vertical semi-axis in this case. Now the centre point is going to be the midpoint of the line joining the foci, right, which is 6i and minus 2i. Therefore, if you add them up and divide by 2, 6 minus 2 is 4, half of 4 is 2, it's going to be 2i, or 0 and 2 on the y-axis. That's the centre point. So now, we've got our centre, we've got our B, the only thing we need is A, and you do that with some Pythagorean skullduggery. And here it comes. Here it comes. It's very beautiful too. So there's that little red cross, that's the centre point, and I've marked in bits and pieces. Okay, so now, so check out our little our Pythagorean triangle here. What have we got? Okay, we've got this unit here, this distance here from the centre up to here is 4. Okay, right? Is that right? That's 4 units. Okay, 4 units from the centre to the focus. Okay, do you agree? Okay, so then the hypotenuse of this triangle here is 5 units. Therefore, you can tell me very quickly what this is here. Yeah, it's going to be 3, isn't it? Of course, it's going to be 3. So therefore, we can say by Pythagoras' theorem, formally writing it out for you, we can say that 5 squared equals 4 squared plus a squared. Therefore, a is going to be 3 for you and me. So therefore, we've worked it out. We've worked it out, haven't we? Yeah. So therefore, we can put that in. Okay, this is our 3 squared, our B was 5, remember that, because up here, yes, half of that number, and the centre point was at x is 0 and y was 2, so there's our ellipse and we've got it. Thank you, Mr. Box. How beautiful is it? Now, I don't know, I can't remember whether I did that one. Oh yes, alright, here we go. This is traumatic. Here we go, take a chill pill. Algebraic method, here we go. We're saying that the distance between 6i and negative 2i is 8 units, therefore that's our initial checkaroonie, and 10 is greater than 8, yes, so we've got an ellipse. That's the very first thing you always do, ladies and gentlemen. Okay, so therefore, we're going to do the old here we go again thing. So putting that into the ducklings all together, the reals and the imaginaries, they're together, all having a lovely time this fine weather. And we're going to Pythagorate it. There it is. Thank you, Pythag, from your 2,500-year-old grave. And here we go. Now I've taken one over the other side, as you know, otherwise it's going to be a disaster. So we square both sides now, as always, and we go through the motions. Yes. Now, in case you weren't aware, just to emphasise this point again, look, some students get all confused, and when they try to square the right-hand side, they say, oh, that'd be 10 squared plus the square root of this square root term squared. No, it's not. It's a compound term. Okay, it's like an a minus b. And a minus b all squared is a squared minus 2ab plus b squared. So you have to do the same thing here. So it's this thing squared plus 2 times this thing, which has got a minus in front anyway, plus this thing all squared. That's how I got that, okay? So let's just keep going, multiplying stuff out, left, right and centre here. And good gracious me, be careful, get yourself in algebra 4-wheel drive mode and do not be an algebra hero. Cancel the x squareds, cancel the y squareds, nothing else cancels. Mop up. Mop up. Right, okay, does that look right? Yeah, minus 16y. Yes, it does. Now, look for the common factor. Always look for the common factor, or else you're going to get telephone numbers when you square that again. Now, what's the common factor? I think it's got to be 4, don't you? Don't you? Yes, I think so. So, therefore, let's go with that. So, okay. Yeah, well, there's one more step now to get all the all the numbers. Yeah, take that 25 from the right-hand side over to the left-hand side, you get that. Now, I still don't like the look of it much. It's going to square out to be pretty awful. Anyway, let's go. Square both sides. Goodness, that left-hand side's a worry. 16y squared plus... where's my chill pill? Oh. Okay, let's go. Yes, yes, little helper, we know. Have another aspirin. There we go. There we go. Yuck. Okay, come on, we're going to clean up quickly. So, this is what we get. Okay, 16 minus 25 is minus 9y squared. 136y minus 100y is 36y. Minus 25x squared, and then you've got 289 minus 100 is 189. Looks all right. Now we have to complete the square with the y term, which is comforting because we know that the y point of the centre is not on the origin, so that's looking good. And remember to divide by 9 and put the middle term in there. Actually, I took out a minus 9, didn't I? Yes. And I got that. Okay, that's looking good now. Okay, so half that is 2. 2 squared is 4, so I need a plus 4 and then a minus 4 in there on the next line. Very good, very good. Now, I have to get this little beastie out of that bracket because I don't want him. He's the leftover bit. Okay? Yeah, good. And remember to multiply him by 9 because he's multiplied by 9. So it gets you minus 36. Okay, this is looking much better now. I think we're out of danger. Yes. Oh, look at that. Okay, so 189 and 36 is 225. Take it over the other side, it's plus 225. Good. Now, that's good. That's going to get us exactly what we want, guys, because dividing by 225 will render some miraculous results. Miraculous results. Okay, here it comes. Beautiful, beautiful, beautiful. Beautiful. Oh, yes. Look at that. Now that is the same equation as we got so easily geometrically. So why would you ever do this? Just to gain confidence and gain understanding. That's why you would do it. Okay? But you don't have to do it in... Yes, yes, yes. Poor little fellow. Don't worry. Go and have a lie down. That might make you feel better. Alright, for graphing purposes, we have to find the intercepts because this beast is not on the centre. Okay, that's a bit more troublesome. Now for the y, it's easy because the y semi-axis was 5. Therefore, we plus 5 to go up from the centre point and minus 5 to go down from the centre point, and you get 2. Y is 2 is the centre point. So you're minusing 5 to go down to the lower bit, which is minus 3, and you're plusing 5 to get to the upper bit, which takes you to 7. Now the x-intercepts, they're not so nice. They're not so nice because I've already done them, guys. So therefore we get, right, now that 4 over 25, where did that materialise from? Oh, that came from here, when y was 0. 2 minus 2 all squared is 4. 4 over 25, okay, now we're going to solve it for x. Okay, so, right, 1 minus 4 25ths is 25 25ths minus 4, which is 21 25ths. Multiply that by 9 and take the square root, and you get something truly ugly. Yes, gurky. Alright, so x is plus or minus 3 root 21 over 5, just to keep us alive. And for graphing purposes, I like to work that out on the calculator, so I just get the thing looking right on the axes. Alright, over the page, and we'll have a look at it. Good gracious me. There it is, and there's my x-axis, x-intercepts I mean, sorry, and there's my centre point. And you don't have to write the centre point in if you're writing formally graphing these things. They don't require you that. They do require the intercepts though. So there's your lower vertical intercept, and there's your upper vertical intercept, and you can see that this is the exact equation that we got. You see? So we've got to the Cartesian equation for a vertically based ellipse, okay, where the centre and the foci reside on the vertical semi-axis, yeah? Okay, oh look, he's recovered. Isn't that nice? Hello, little helper, you've had to lie down on your aspirin. Oh, isn't that good? So everything's good again, it came to a happy ending. And I hope you're feeling happy, because I am, because we've just concluded our ellipse, our beautiful oval bent circle extravaganza. And the last session next time is going to be on the magnificent and mysterious hyperbola. So I know you can't wait, and we'll see you then. Okay, bye for now.